We're given z equals the quantity x squared minus 4x times the quantity y squared minus 2y. We want to classify the critical points as local maximums, local minimums, or saddle points. To find the critical points, we'll determine where the first order partial derivatives are both equal to 0 or where either does not exist. Once we find the critical points, we'll determine the value of d using the second order partials, and then based upon the sign of d and the sign of the second order partial with respect to x, we can determine whether we have a relative min, relative max, or saddle point at the critical points. Let's begin by determining the first order partials. So the first order partial with respect to x will differentiate with respect to x, treating y as a constant. We don't need to multiply this out because notice how we have just x terms here and just y terms here. So when differentiating with respect to x, we're treating this as a constant. And since the derivative of x squared minus 4x is 2x minus 4, we would have 2x minus 4 times y squared minus 2y. And then for the partial with respect to y, we'll treat x as a constant and differentiate with respect to y. So now this is a constant, and since the derivative of y squared minus 2y would be 2y minus 2, we have x squared minus 4x times 2y minus 2. We also need the second order partials later, so let's find those now. The second partial with respect to x will differentiate this partial derivative, again with respect to x, treating y as a constant. The derivative of 2x minus 4 with respect to x would be 2, giving us 2 times the quantity y squared minus 2y. For the second partial with respect to y, we'll differentiate this partial derivative with respect to y again, treating x as a constant, differentiating with respect to y. So this would be a constant. The derivative of 2y minus 2 with respect to y would be 2, so we have 2 times the quantity x squared minus 4x. And now for the mixed partial, with respect to x and then y, we'll differentiate this partial derivative with respect to y, treating x as a constant. So we'd have the quantity 2x minus 4 times the derivative of y squared minus 2y with respect to y, which should be 2y minus 2. And now to find the critical points, we'll set the first partial derivatives equal to 0 and solve as a system of equations. In the sake of time, I've already set some of this up. Here are the first partials. Notice how we can factor these further. We can factor out a 2 here, which I show here, factor out a y here, which we see here. So you can rewrite this as 2y times the quantity x minus 2 times the quantity y minus 2. And for this other partial derivative, we can factor out x here and factor out 2 here. So we can write this as 2x times the quantity x minus 4 times the quantity y minus 2. So this may seem like a challenging system to solve, but we can take advantage of the fact that it's in factored form. For example, looking at this first equation, notice how if y was equal to 0, this equation would equal 0. So we'll find one critical point where the y coordinate is 0. Well, notice if y is 0, and we need the second equation to also be 0, if y is 0, x could be either 0 or positive 4. So this actually gives us two critical points, the point 0, 0 and the point 4, 0. Now going back up to the first equation, notice how if x equals positive 2, this would be 0. So if x is positive 2 in the first equation, this would be 0. So now we'll ask, what does y have to be in the second equation for this also to be 0? Well, if x is 2, y would have to be positive 1 in order for both equations to be 0. So now we have 3 critical points, but there's more. Going back up to the first equation again, notice how if y is positive 2, this equation would be 0. So if we make the y coordinate positive 2, let's see what x has to be in the second equation for this to be 0. Well, if y is positive 2, notice how x can be either 0 or positive 4. So this actually gives us 2 more critical points. Again, if y is positive 2 in the first equation, that would be 0. So x can be either 0 or 4 in the second equation, giving us a total of 5 critical points. So now we'll use these critical points in the second order partials to determine whether we have relative max, mins, or saddle points at these locations. And again, to save time, I've already set a lot of this up. Here are the 5 critical points that we just found. And now we need to find the value of d using this formula here and the second order partials that we found on the previous slide, which I've copied here. So we're going to evaluate the second order partials in this formula using our critical points. So for the second order partial with respect to x, at these critical points, this represents the value of each. And then for the second order partial with respect to y, these would be the values. And then for the mixed partial squared, using this mixed partial derivative, these would be the values. Again, you may want to pause just to verify that I set this up correctly, but let's go ahead and evaluate these. Well, here we'd have 2 times 0, which would be 0, times this would also be 0, and then we have minus, this would be negative 4 times negative 2, that's positive 8 squared, which is equal to negative 64. And since d is negative or less than 0, notice how that means we have a saddle point at this critical point. At the point 4 comma 0, notice how this would be 0 times, this would be 16 minus 16, so that's also 0, minus, here we would have 8 minus 4, that's 4, times negative 2, that's going to be negative 8 squared, which is still negative 64, which is less than 0. So at the point 4, 0, we have another saddle point. At the point 2, 1, here we have 1 minus 2, that's negative 1 times 2, that's negative 2, times, this would be 4 minus 8, that's negative 4 times 2, that's negative 8. And then we have minus, this would be 4 minus 4, that's 0. This is also 0 squared, so we have minus 0. So this is equal to positive 16, which is greater than 0. So because d is greater than 0, and the second partial with respect to x is negative, that means we have a relative maximum at this critical point. At the point 0, 2, we'd have 4 minus 4, that's 0. Here we have 0 as well, so we have 0 times 0, minus, here we'll have negative 4, this is 4 minus 2 or 2, so negative 4 times 2 is negative 8, but we're squaring that. So this is negative 64, which is less than 0. So again, we have another saddle point at the point 0, 2. Finally, at the point 4, 2, here we'll have 4 minus 4, so that's going to be 0, times, this would be 16 minus 16, that's 0, minus, here we have 8 minus 4, that's positive 4, times 4 minus 2, that's 2, positive 4 times positive 2 is 8, 8 squared, again it's negative 64, which is less than 0, so once again we have another saddle point. So we have 4 saddle points and 1 relative maximum. So when a homework says classify the critical points as local max, mins, or saddle points, the local maximum is at the point 2, 1. There are no local minimums. I think our homework asked us to type in DNE for this, and there are 4 saddle points at the remaining 4 critical points, which again were 0, 0, 4, 0, 0, 2, and 4, 2. Let's finish by looking at the surface in 3D. It's a fairly complicated surface, but one thing we should be able to see is this high point over here, which is the local maximum. We can also see there are several saddle points. If we wanted to find this relative maximum function value, we would have to evaluate the function at the point 2, 1. It doesn't ask us to do this, but I do want to point out that f of 2, 1 is equal to positive 4, so the local maximum value is 4 at the location of 2, 1. I hope you found this helpful.